So our first speaker, Koushik Venkatesan, will speak about a new class of highly tunable and efficient emitter systems. So when you're ready, please.
Thank you, Philippa. Thank you very much. I would like to thank the organizers for this kind opportunity to present our group's work, and good afternoon to everybody. So what I'm going to tell you today is our group's foray into this new class of emitter systems, which has carbenes as ligands and metal as platinum 2. So before I go into like today's talk, I would like to give an overview of our research that is ongoing in my group. So we work on actually platinum and gold, platinum 2, platinum 4, and gold 3 cyclometal-related complexes, mostly focusing on, at the moment, carbenes as ligands, focused towards OLED applications. The other aspect my group works on is in the developing main group chemistry, mostly boron compounds, and trying to make donor acceptor systems, again, to trying to achieve thermally activated delayed fluorescence from these molecules. And the third aspect is what we are trying to do is develop a redox active molecular systems and trying to measure single molecule charge transport across these molecules in collaboration with IBM, and trying to then translate this into large scale molecular electronic devices. So before I go into the details of today's talk, I would like to first really thank my research group, the students who did this work. They're highlighted in blue, who did this platinum to N-Heterocyclic carbene work. And I would like to thank all the collaborators here for DFT and crystallography, Dr. Olivier Black from University of Zurich, and also Chung-Chi Wu from Taiwan for the device work, and for the funding, Swiss National Science Foundation, University of Zurich, and Macquarie University. And I would like to really mention that without all these students' work, I wouldn't be standing here to present this work. So the credit really goes to them. So our group for the past 10 years have been focused towards developing gold 3 cyclometal complexes, and as well platinum 2 based triplet emitter molecules for OLED applications. I don't think this audience needs any significant introduction and motivation. The advantages of OLEDs being brighter, thinner, and high contrast flexible displays. One of the key thing for OLEDs is the challenge is to get to make a white light. Of course, the aim is to reduce energy cost for lighting. And the other interesting aspect of creating white light from OLEDs would be to make tunable white light as well. Now, our key focus of my research group is on making the dye molecules for these OLEDs. And many of you are aware that the typical molecules that are being used in OLEDs are these iridium cyclometal complexes and the platinum cyclometal complexes, what you see on the right-hand side. Now, if you look at this, most of these complexes, they are actually have either a bidentate ligand core or a tridentate core. And one of the widely held dogma in the field is that you need actually a strong chelating ligands, or either bidentate, tridentate, or tetradentate in order to improve the efficiency of these systems. And one of the critical things that is driving OLED research at the current moment is the lack of deep blue and blue emitters in the field. And these are some examples of what is out there. And again, what you see in common among these complexes is that they have a bidentate ligand system, a cyclometal ligand system around them, or in this case, a tetradentate systems as well. So these are actually the typical complexes that are being developed. And most of the complexes here have blue emission, but as you can see from this chart, that only very few appear in the deep blue region. So one of the things when I started my research career, I took this as a challenge, and one of the hypotheses is to not to make cyclometallated compounds, to move away from actually cyclometallation and to involve monodentate ligands and build the complexes. So the idea was to build a square planar complex with N-Heterocyclic carbenes and in combination with alkyne ligands. Now, one of the advantages of these N-Heterocyclic carbenes, they are very strong sigma donors, and they are a very soft ligand, and so that means they are going to bind to the soft metal center, such as platinum, very strongly. So that should give stability. The other interesting aspect of N-Heterocyclic carbene is that the sigma donor effect of the N-Heterocyclic carbene would destabilize basically the LUMO, and that thereby you have creating a larger homo-LUMO gap. And of course, now what was evident at the start itself, that the N-Heterocyclic carbene such as this is not going to be involved as part of the chromophore. So the chromophore has to come from this ancillary alkyne ligand. And of course, one key thing is that these alkynes need to be trans to each other. Otherwise, they are disposed to reductive elimination if these two alkynes would be cis to each other. Now, if we look at literature, I think most of the people here are aware of the phosphine, platinum phosphine dialkyne complexes. Quite a lot of work has been done on this fragment. And later came this pyridine complexes, and there are also bipyridine platinum dialkyne complexes as well. Now, depending on the donor ability and the acceptor ability, so most of these compounds, with the phosphine and the pyridine, the emission usually appears in the green or the red part of the electromagnetic spectrum. So, and one of the other aspects of these, where the quantum yields of these compounds are rather very, very low, and there have not been much really applied in OLED devices. Now, what was our thought process here in introducing the carbene is that this would lift the metal center triplet excited state much higher, so that it creates an inaccessibility of the population of this and creating a non-radiative decay pathway. So when you compare with the phosphine and the pyridine ligand, and of course, as I said, because you destabilize the LUMO, so your homo-LUMO gap as a consequence is also larger. So thereby you have an opportunity to obtain blue emission. Now, so I'm going to present it in a very chronological order how we did this chemistry. So although our target was this trans molecules, so there was not much synthetic procedure out there. And there was a paper published in Organometallics that showed that the cis dichloride, which you would need to make the dialkyne complex, is actually the thermodynamically stable product, rather the trans dichloride, platinum dichloride bis carbene complex is actually the kinetic product. So there was no suitable starting material that was available. So what we were trying to do, we were trying to explore then in the meanwhile to see how our hypothesis developing blue emission based on these carbene complexes would work, because there was not much in literature at all on these kind of dialkyne carbene complexes. So we started with this nice work. Actually, we used a work of Professor Thomas Strassner from Germany. So he had developed this carbene platinum diiodide complexes using this platinum bis ACAC as the starting material. And this synthesis of the starting material works very nicely. Now, we took the starting material, this diiodide complex, and treated with the corresponding lithium acetylide and generated a number of cis dialkyne complexes. Of course, I think one would know that compared to the palladium dialkyne complexes, when they are cis to each other, the platinum dialkyne complexes are relatively more stable. So one could actually easily isolate them, and all this chemistry has been done on the bench. You don't need any glove box. They are very stable. Now, using this addition of the lithium acetylide, we were able to generate a number of dialkyne complexes with really good very good to moderate yields, depending on what kind of alkyne one uses. Now, here is the photophysics of these complexes, and here is the absorption spectra. Now, as you can see here, as we change the donor groups on the phenylacetylene here, so you have a red shift in the absorption spectra. And as you can see here in the emission spectra as well, there's a corresponding shift in the emission as well with respect to the donor groups. And as we had expected with the carbene dialkyne complexes, you can see the emission at around for the phenyl acetylide functionality. So you see it's around 430. So that was very encouraging that these dialkyne complexes indeed have like deep blue emission, show deep blue emission. Now, based on our initial results, one of the things what we wanted to understand, what is the influence of the different electronic properties of these carbene ligands. So, and we had looked a combination of pyridine and N-Heterocyclic carbene, and we had used triazole with different substitution pattern. You see, for example, 124 and 134. And what we had found actually that we were able to improve their quantum yields up to 30% in thin films. Of course, 30% is not something to really write about, but this was something in the right direction. So having understood that, we then came on to this identifying a synthetic pathway to make the trans complex. So of course, we did not take the dichloride. We took a very different approach. Now, what was that approach? So now when we took this platinum cord dialkyne phenyl complexes, and when we treated this dialkyne complex with 2 equivalents of the N-Heterocyclic carbene in the presence of potassium turbotoxide, what we generated was 9% trans complex and 27% cis complex. Okay, now these were cleanly separable by column chromatography. Now, when we increase the stoichiometry of this carbene in the next reaction, we obtained less of the trans and more of the cis. So this was suggestive of the cis complex being the kinetic product and the trans complex as the thermodynamic product. So that is something for us was very good. Now, 2%, 9%. So how do we go from there? And one of the interesting thing was it had the NMR, 1H NMR of this trans complex and the cis complex had a very characteristic splitting pattern for these protons that was attached to this carbon, which in turn was attached to this nitrogen. So that was something for us very distinguishable and easily characterizable of these complexes. Now, one of the things what we did was we took this complex, the cis complex, and then we threw in 10 mole% of this platinum cord dialkyne complex and left it for really followed the reaction. And after 7 days, we obtained 64% of the complex. Of course, it's a very expensive reaction. You take platinum and you put platinum and you make platinum, so you lose a lot. So it becomes a very expensive reaction and it takes 7 days. So that's not something that's ideal. Now, we found 2 other methods for that. Now, what we did was we took this complex in neat solid and we heated this complex to around 200 degrees and we obtained the trans complexes in very high yields. Or we could take this complex in toluene, the cis complex in toluene, irradiate it under ultraviolet conditions and obtain the trans complex as well in reasonable yields. Now, so what's going on? Basically, when we heat this, when we take this complex, we don't add anything at all. How do we get the trans complex in very good yields? Now, it took us nearly a year to work out this mechanism because the cis-trans isomerization presented here, the kind of mechanism is previously unknown. So this is our proposed mechanism. So here is the cis dialkynyl complex. In a first step, when we heat this complex at 200 degrees, what happens is it reductively eliminates in this butadiene compound. Now generating a little bit of this platinum 0 complex. Now this platinum 0 complex then associates with the cis complex, forming this kind of a transition state, and then undergoing Berry pseudo rotation in 2 steps to then eliminate the trans complex and generating the platinum 0 again. So that is why we need a little bit of decomposition. The reason one needs to heat this complex at 200 degrees, because the cis complex is that stable. So it starts to decompose only at 200 degrees to generate this platinum 0, which is the active catalyst to enable this conversion. Now, before I proceed, we did look at very different scenarios. And we disproved like the dissociation of the carbene. So that was not the case. That was not the case because we did use labeled carbene as an external source to see if there was an exchange of the ligand. We did look at, for example, here the dissociation of the alkyne, and calculation showed the activation barrier is way too high than what you need, what we are using at 200 degrees. So we ruled out the possibilities. We had looked at solvent coordination alone to enable this cis-trans isomerization, which was not the case as well. So finally, we came to this proposal of the cis-trans isomerization. Now, so these are the cis compounds, and the photophysics was similar to the other chelated carbenes. Now, this is a fluorinated benzene and fluorobenzene, and as you can see, depending again on the donatory ability of this on the phenyl ring, the photophysics, the absorption as well as emission pretty much shifted to the red. Now these are the trans complexes, and both the absorption spectra and the emission spectra was very similar to the cis complexes, except for a 2 nanometer shift with respect of the trans complexes towards the red. This is like very consistent across the measurements, a 2 nanometer shift of the trans complexes versus the cis ones. Now, what is actually interesting, so is what you see here is like the what we made. We took 5-8% of the complex and spin coated, doped it into polymethyl methacrylate plexiglass, and did some measurements. Because one of the things these complexes, one has to mention that they have very low quantum yields in solution. That is because, of course, there are 2 answers for that. Why is the case? Because you have, of course, these are rotations that is causing non-radiative decay. The other one, the excited state, is being quenched by the solvent. So these 2 are attributed for their low quantum yields in solution. However, now when we dope these molecules into thin films, make thin films, they have pretty reasonably good quantum yields. Now the cis has a quantum yield of 60.8, and you have a wavelength of 425. And 447 is normally the shoulder. The redmost band is the shoulder. This one is the main transition, what you see. And as you can see, the cis complexes, of course, unfortunately, has the higher quantum yield than the trans consistently actually across the board. And what we can also see here is that we are able to make something that is emitting in deep blue. So what we went further. We went further and looked at how the change of the electronics of the N-Heterocyclic carbene ligand, here is a triazole, and here's an imidazole, affects again the quantum yields. And as you can see here, in 10 weight % PMMA, you get around 60% quantum yield, and in 2 weight %, of course, 80% quantum yield. Now, one And as you can see, the triazole ligand, as also we have shown earlier, the triazole ligand has a higher quantum yield for these complexes. And you have a strong quenching behavior. Of course, they are square planar complexes. They, as we know, they don't form excimers. They create aggregates where your excited state is then funneled into this aggregates low energy path and creating non-radiative decay. So what are we doing now? So we have taken these molecules and built a device. And the interesting thing is that trans molecules are highly stable. They can be thermally evaporated. And based on this, the group from National Taiwan University, Chung-Chi Wu, he fabricated the device. So here are like devices fabricated based on 2 molecules. And the blue is something very close to the NTSC requirement. And what we also have is basically an EQE of 7.3% and 6.2%. Surely the triazoles outperform. And what we also actually see with these complexes is that, as I showed you before, that there is a very strong quenching effect now, increasing the doping concentration. So what we have actually shown is that we have been able to move away from cyclometallation, which is in some ways it's a kind of a limitation. As you can see, the cyclometallation synthetic approaches, it leads to very low yields. So these complexes are easily accessible, and they emit in at a higher wavelengths with really high quantum yields. And the thermogravimetric analysis study supports high thermal stability of these complexes, and we have shown that it can be thermally evaporated. And OLED devices shows EQEs of 7.3% and 6.2%. And of course, one of the critical things, if you have to look at it critically, so one of the things is that it shows very strong concentration dependence, quenching, and of course the device performance is affected based on that. So that is something we will need to improve, and we have strategies in place to improve, because we can introduce bulky groups in at the nitrogen here. We can also introduce bulky groups at the at this distal position to the platinum. So we do have certain handle to separate these intermolecular interactions. So the other key thing at the moment is these complexes have still a large microsecond lifetimes. And so that is something would cause triple annihilation. The other one is device roll-off efficiencies as well. So that's one thing we are trying to, at the moment, address, looking at very different carbenes and different ancillary ligands. To address this KR, the radiative rate, we are looking at something targeting something in the order of 10 to the power 6. And still trying to improve their quantum efficiencies with the radiative rates being increased. Now, what we are trying to do is exploring these carbenes. For example, here in the case, what we have shown that a combination of pyridine and carbene conjugated using this bidentate ligand and changing the alkynes, what we are able to create is excimers. And now what we are trying to understand systematically is how to influence excimer formation and further shift this excimer formation to near infrared and build near infrared emitters based on this platinum N-Heterocyclic carbene fragment. So thank you very much. Happy to answer any questions.
Thank you very much. If anyone has any questions, can you please unmute your microphone and speak up?
Yeah, it's Paul Byrne.
Hi, Paul.
Hi, Koushik. Thanks very much for your presentation. I have a question relating to your devices.
Yes.
So you showed us very nicely about the concentration dependence of the photoluminescence quantum yield. Can you just go back to the device slide for us?
Yes, absolutely. Just a second. I'll need to go to share. Just a second. Yes. Is this one? Or
the device architecture, actually. So you've got a whole bunch of things in there. And the emissive layer is the DPEPO microbac, da.
correct. So sorry, this is the name of the compounds we gave it to our collaborator.
Yeah, no, that's cool. So do you know what the PL quantum yield in that thin film is? Because PMMA has a completely different dielectric constant to that combination materials. And the dielectric constant will have an effect on the PL quantum yield and the radiative and non-radiative decay rates. And of course, DPEPO is actually a phosphorus or phosphine oxide based material, which can also, I guess, be considered almost as a ligand or potential ligand as well. So do you have a feel for what the PL quantum yield is for those that emissive layer?
Yes, so the quantum yields have been measured, and actually it surprisingly matches with the PMMA in this case.
Okay, yeah.
So that's very interesting, and you can say maybe it's lucky, but in this case, but yes, so the quantum yields were found to be similar,
right.
Very close, but very strong. I think they did a lot of studies with the DPPO for the concentration dependent studies. We didn't do much more, we didn't go about 10%. So they did until 16%, and you could see very strong quenching effects.
Right. So with the quenching effects, do you also see a, well, from the data you showed, it didn't seem like it, but you seem to have a, often you see a red shift in the emission.
Yes. So we didn't see actually, so that's one interesting thing. And at the moment, I did tell you that we are working on excimers. So that's one thing what we didn't see that much in this case. We didn't see, any broad shoulder, like let's say going up in intensity. So because that's something also I was looking, if we can develop excimers based on this, but unfortunately you see only quenching.
Right, okay.
Yeah.
Presumably that's because you've got the alkyl groups, which are sort of orthogonal to the rest of the plane, and that sort of holds them apart a bit.
Yeah.
Okay. All right, thank you very much.
It's a pleasure, thank you.
Were there any other questions very, very briefly? We're pretty much out of time, but if anyone has a quick question, if not, everybody